Welcome back to the Deep Dive, the shortcut you need to grasp the most complex, cutting-edge tech in generative AI. Today, we are strapping on our engineering hats because we are embarking on a high-fidelity, highly technical deep dive into diffusion models DMs.
That's right. For you, the learner, our mission is to move past the dazzling images and videos you see produced by models like Stable Diffusion. We need to go straight to the foundational mathematics, the score functions, the differential equations, the optimization targets that truly define how these models work.
Yeah, get under the hood.
Exactly. We want you to understand why DMs are fundamentally different from models like large language models, the ones built on the transformer architecture.
Right. We're not just looking at the architecture itself, we're examining the history. Because the success of DMs isn't just one brilliant idea that popped up. It was more like this massive convergence, a foundational triad, where three, pretty distinct mathematical schools of thought proved to be mathematically equivalent, all pointing to the same core idea.
It's actually one of the most elegant stories in modern machine learning, I think. Before the recent breakthroughs, you had researchers in like 3 different fields developing separate methods for generative modeling, rooted in different historical models, different starting points. But today, they pretty much all unify under the SCORE SDE framework.
Okay, let's break down that triad. Where do we start?
Well, let's start with the first branch, the variational perspective. This is the lineage that gave us maybe the most famous early success. DDPM, denoising diffusion probabilistic models. Its roots are in the world of variational autoencoders, VAEs, and their more complex hierarchical cousins, HVAEs.
VAEs. Okay, so thinking about maximizing likelihood.
Exactly. That view is rooted in maximizing the likelihood of the data, PX. In the VAE tradition, calculating the true likelihood is intractable, so you maximize a lower bound instead, the evidence lower bound, or ELBO. It's a guaranteed surrogate. In DDPM, the process gets split. The forward process, the part that adds noise, is treated as a fixed, non-trainable encoder. You don't learn that part. The reverse process, going from noise back to data, that's the learned decoder.
And here is the profound simplification that really made DDPM take off, wasn't it? They didn't try to optimize the full, messy ELBO term.
That's the key insight. Exactly.
Yeah.
They showed that a specific simplified surrogate loss, known as L-simple, works incredibly well. And L-simple is mathematically equivalent to minimizing a mean squared error, an MSE loss, on the injected noise epsilon.
Just the noise?
Just the noise. The model is simply trained to predict the noise epsilon that was added to the image to create that noisy state $6. This means the entire really complex problem of density estimation and maximizing a variational bound. It just boiled down to a simple, stable regression problem.
Right.
Predict the noise you added.
Wow. Okay. That simplicity and stability, that sounds like the key.
It really was.
So the second lineage, where did that come from?
That's the score-based perspective.
Yeah.
And this came from a completely different direction. Energy-based models, or EBMs.
Ah, EBMs. Conceptually elegant, but computationally tricky, right?
Tricky is an understatement. Computationally disastrous might be closer. EBMs define the probability of data using an energy function. PS as proportional to E phi.
Okay.
The problem is the normalizing constant needed to make probabilities sum to 1. The partition function, calculating Z phi, involves integrating across the entire massive high-dimensional space of potential inputs.
It sounds like trying to calculate the exact volume of a mountain range on a planet with infinite dimensions. It's just totally intractable.
It is. The computational cost is immense, and it was a major roadblock for EBMs for a long time. Score-based models, like NCSN, noise conditional score networks, solve this by completely bypassing the density PX and the partition function phi. They realize they don't actually need the density value itself. They only need its gradient. Specifically, the gradient of the log density, which is the score function, Black's log.
The gradient of the log, okay.
And since the score function is derived from the log density, that intractable constant V phi, because it's just a constant factor, it drops out during the differentiation.
Ah, clever. It just vanishes.
It's an incredibly elegant mathematical bypass. Really neat.
So if the variational approach simplified the likelihood optimization down to noise prediction, the score-based approach just sidestepped the intractable normalization problem altogether.
Precisely. 2 different ways to make the problem tractable.
Okay, and the third lineage, the one that ties it all together.
That's the flow-based perspective. This is where we really bring in the physics, treating the generative process not just as discrete steps, but as a continuous flow over time.
Right, continuous time. So differential equations.
Exactly. Stochastic differential equations, SDEs, and ordinary differential equations, ODEs. They model the entire path from data to noise and back again. Generation is seen as solving a differential equation flow that transports samples smoothly from a simple prior, like a standard Gaussian n dollars, toward the complex data distribution.
And this is the SCORE SDE framework you mentioned.
Yes, it reveals that both DDPM, the variational view, and NCSN, the score-based view, are actually just specific discretized versions of the same underlying continuous flow. It's the unifying picture.
Okay, let's unpack this core mechanism then, because this is where the physics of generation really happens. It starts with the fixed-forward process, data to noise. You said it's fixed, rigid, and actually pretty simple.
Surprisingly simple, yeah. The forward process is essentially a carefully controlled destruction process. We take our original data point, $6.11, and we progressively corrupt it by adding Gaussian noise over many steps, or continuously from time to t-colors. And this is crucial. The transition kernel, its continuous equivalent, is known, simple, and fixed. We don't train this part.
And the goal here is vital, right? After time tilers, the final state, $6, needs to converge exactly to a simple known distribution, usually that standard Gaussian $3.
Exactly. It shouldn't matter if $6 was an image of a cat or a dog or a boat. $6 must be pure, homogeneous noise. All information about the original data is destroyed.
And in continuous time, this gets formalized by the forward SDE. You wrote it as SEST TDT plus GDT DWTD. This is where the physics analogy really kicks in, describing how the state evolves over a tiny time step TD dollar.
But let's break down those two components because they're key. First, you have the deterministic drift term, FXTT.
Okay, the drift, what does that do?
The drift term dictates the deterministic push. It's how the average or expected value of the state changes over time. If you ran the process many, many times from the same starting point, the drift determines the path of the mean of all those runs. Often, this term scales the current state down over time, ensuring the overall magnitude collapses towards zero, towards the center of the Gaussian.
Makes sense. And then you have the really crucial stochastic element, DDTT, DWT2, the diffusion term.
Yes. So GDT is the diffusion coefficient. It controls how much noise is being injected at any given time, $2. Often it increases over time. And DUDT is the Wiener process, or standard Brownian motion. This is what introduces the randomness, the stochasticity.
Or random walk part.
Exactly. Unlike a standard ODE, which would give you a single predictable outcome from a starting point, the SDE includes this random variable dollars. It means every run of the forward process, even starting from the exact same $6 dollars, will result in a slightly different sequence of noisy samples, $6. This ensures the corruption process is non-deterministic and thoroughly explores that final noise space.
Okay, so that's the encoding part, smashing data into noise. Relatively easy because we define the rules. Now comes the magic, I guess. The learn reverse process. Noise to data. How on earth do you learn to reverse a non-deterministic, noisy path like that?
This is where the really advanced math comes in, specifically time-reversed SDEs derived from ITO calculus. It's pretty deep stuff. But the theory dictates that any SDE, like our forward process, can be reversed, provided, two things. One, the forward coefficients are $5, we know those, we define them. And two, the gradient of the log density of the intermediate distributions, PTX, you get at every time.
Ah, and that gradient of the log density, that's the score function again.
Exactly. This leads directly to the structure of the reverse SDE. Looks like this. PTXC2T plus GTF sub plum. Look closely at that equation. The entire reverse process is governed by known terms, are $500, except for that single critical piece of information, the score function, TXCT, which is IRDAC called P, N, and K.
So everything hinges on estimating that score function.
Precisely. The score function is the only unknown component required to reverse the process. If our neural network can learn to estimate the score accurately for all relevant points, $6 and times $1, we can effectively run this SDE backwards and generate samples from noise.
Okay, but intuitively, how does the score function actually guide the process back? What's it doing?
Think of it like a force field, or maybe gravity on an energy landscape. That's a common analogy. At any point $6 on any time today during the reverse process, the score function 6tux is a vector. It points in the direction where the probability density PTS increases most steeply, locally.
So uphill on the probability landscape.
Exactly. As the noisy sample flows backward in time from $2 to $10, the score function locally guides it, pushes it, back toward the areas where the data is more likely to live the low-dimensional manifold where the clean data resides. It's constantly calculating the direction of steepest descent in probability. And that 2D2 dollar term in the reverse SDE. That scales this guidance relative to how much noise was being added at that time, $2.
So the network isn't learning to reconstruct the image pixel by pixel directly. It's learning a directional field, a set of instructions that tells the noise particle where to move next to increase its likelihood of becoming clean data.
That's a great way to put it. It's learning the flow lines. And this insight that the score function is the key is what allows us to transition from this stochastic process back to a potentially deterministic one, which is vital for speeding things up. This brings us to the probability flow ODE, PFODE.
Wait, hang on. If the reverse SDA you just showed us is stochastic, it still has that random term. How can we just switch to a purely deterministic ODE without losing something? Doesn't the randomness matter for generating diverse samples?
That's a really sharp question.
Mhm.
It feels like we should lose something, but it turns out we don't, thanks to some mathematical elegance. The key is that we are looking for a deterministic flow, an ODE, that transports the probability mass along the exact same time-dependent marginal distributions PTX as the reverse SDE does. And such a deterministic flow exists. The score function, Malebach's log, PTX, implicitly captures the average effect of the noise at each instant. So the PFODE is essentially the expected or average trajectory of the reverse SDE. Since the score function precisely describes the gradient of the distribution, the flow can be defined deterministically without changing the marginal distributions, t-tellers, at each time.
So the PFODE basically removes the stochastic term and compensates by adjusting the drift term. The PFODE drift is defined as VST, FTX, frax12 TSX, using the optimal score sounder.
That's correct, and this transformation is absolutely pivotal. When we sample from a diffusion model, especially when using these faster, more modern samplers, we are not performing autoregression like a transformer does, predicting token by token. We are numerically solving a differential equation. We're integrating a path through time and space.
That feels like a fundamental difference.
It is. It fundamentally separates DMs from LLMs. DMs integrate a global continuous function defined by the score. LLMs step locally through a discrete state space based on conditional probabilities. Very different mechanisms.
Okay, so the genius here is converting this like impossible density estimation problem into something tractable, predicting the score function. Let's dive deeper into how we actually train the network to estimate that score function XX at $2. You mentioned score matching.
Right, so let's revisit EBMs and that partition function Z-Phi disaster. To really grasp the scale of that problem, imagine trying to estimate the probability of a single high-res image, say 24 by 124 pixels. That probability depends on the energy of that specific image relative to the summed energy of all possible 124 by 124 images.
Which is astronomically huge.
Mind-bogglingly huge. Z-Phi is that sum, that integral, over the entire input space. In high dimensions, the volume of possible states is just too vast. The integration is effectively impossible.
But the score function comes to the rescue again. Lablax EXSE, and that calculation is completely independent of that horrifying normalization constant Z-Phi.
Okay, exactly. That's the foundation. But there's another catch. If we just tried to estimate the true score of the raw data distribution, Knobloch-Milo, we'd run into major stability issues.
Why is that?
Real data, like natural images, tends to live on a very thin, low-dimensional manifold embedded within the massive high-dimensional pixel space. Near that manifold, the probability density changes incredibly sharply, almost infinitely fast. This makes the score function itself unstable or mathematically ill-defined right on the data manifold.
Okay, so you can't calculate the gradient reliably right where the data lives. We need to, what, smooth it out somehow?
Precisely. We need to smear out the data a bit. And this brings us back perfectly to denoising score matching, DSM.
Ah, using the noise again.
Exactly. DSM solves this stability problem by leveraging the forward diffusion process itself. By adding known amounts of Gaussian noise, controlled by sigma, or time $2, we move the problem away from that unstable, thin data manifold. We perturb the data points $6 into $60. This creates a smoothed-out distribution P sigmas, which is nicely defined across the entire space, not just on the manifold.
Okay, so you're estimating the score of the noisy data now.
Right. DSM works by minimizing the mean squared error between the model's predicted score, let's call it sigma, and the true score of the noisy data distribution, Knobloch's log P sigma. This objective turns out to be tractable and stable, providing a solid loss function that allows large neural networks to learn this directional field effectively.
So it's essentially a stable, well-defined regression target for the network. And this mathematical cleverness is what allows those two original lineages, DDPM from the variational camp and NCSN from the score-based camp, to actually converge, even though it looked like they were optimizing different things. One was predicting noise, the other predicting the score.
They really do converge, and the formal link is provided by Tweedy's formula. Tweedy's formula provides a direct bridge between the optimal noise predictor and the optimal score function, specifically when the noise we're using is Gaussian.
Okay, give us the core insight of Tweedy's formula here. Why does predicting the noise epsilon equate to predicting the score $6?
The insight lies in conditional expectation. Tweedy's formula states that the optimal score function sigma ballers for the data, perturbed by noise level sigma, is directly proportional to the conditional expectation of the noise epsilon given that noisy data. The formula is ZS pen sigma. Wait, actually, the common form used here relates it to noise prediction target, sigma sigma. Let me rephrase that. The optimal score is proportional to the optimal noise prediction.
Ah, okay. So when DDPM minimizes the MSE for noise prediction, trying to get its epsilon phi to match the true epsilon, it's effectively converging to epsilon, or rather the optimal noise epsilon. And Tweedy's formula shows that this optimal noise prediction, epsilon, is mathematically equivalent up to scaling by sigma to the optimal score, $60.
Exactly. They end up minimizing two different-looking but mathematically tightly linked MSE objectives. It proves they are fundamentally learning to reverse the same underlying physical flow, whether you frame it through the variational lens, predicting noise, or the energy-based lens, predicting score. They are just two different parameterizations of the same core task.
Okay, that's elegant. But despite this mathematical equivalence, they both initially suffered from a shared bottleneck. They were slow. The generation required really dense time discretization, hundreds or thousands of steps.
Yeah, that inefficiency is sort of inherent if you use simple numerical integration methods like basic Euler steps, especially when the function you're integrating, the score, changes rapidly over time or space. This is why the score SDE framework is so important. It clarifies that this is fundamentally a continuous integration problem. And that realization motivates us to bring in the heavy artillery from numerical analysis for solving differential equations much faster. We'll definitely get to that.
Right, faster solvers. But before we accelerate, let's quickly touch on implementation choices. You mentioned the network head, the final layer, can be trained to predict one of four equivalent quantities, the equivalence of parameterizations.
Right. So the neural network doesn't have to predict the score directly. It can be trained to predict. 1, the noise itself, epsilon phi, like an original DDPM. 2, the score, like an NCSN. 3, the estimated clean data, $6 prediction, often called $6, or something called the velocity. And the cool thing is these are all algebraically convertible. You can switch between them using the known time-dependent coefficients, alpha and sigma par, from the forward process noise schedule.
Practically speaking, why choose one over the others? Is there an advantage? You mentioned Vev-Baller prediction, maybe combined with a specific noise schedule?
Yeah, the choice can significantly affect optimization stability and the scale of the target value the network has to predict across time. The Vev-Baller prediction parameterization has become quite popular recently. The reason is when you pair it with the specific type of noise schedule, often a linear variance schedule, where noise variance grows linearly with time, something really nice happens mathematically. The second derivative terms, the curvature effects, and the underlying ODE dynamics, they actually vanish.
They just disappear. That sounds like a huge benefit for optimization.
It is. It essentially simplifies the optimization landscape the network is navigating, makes the learning problem much cleaner. You can think of $5 prediction, especially with that schedule, as training the network to predict the simplest, straightest possible trajectory in a transformed space. By flattening the mathematical surface we're training on, we get a more stable target scale across the whole diffusion time term. You avoid situations where the gradients or target values explode or vanish near the endpoints, or 2 or 2.
Which seems critical if you want stable training, especially if you plan to use very few sampling steps later during inference.
Exactly. It's a design choice that's really geared towards enabling high-speed inference down the line.
Okay, so the stability and quality of these models are impressive, but they became truly transformative, I think, once researchers figured out how to control them, how to condition them on specific inputs. This brings us to conditional diffusion models, CDMs, and the concept of guidance.
Yeah, this was the step that really unlocked the huge practical and commercial potential we see now. Guidance is simply using some external information, let's call it del-I, to steer the generative path. If the model learns the conditional distribution brand, it moves beyond just generating random images to generating specific images conditioned on, say, a text prompt or an input image, a segmentation mask, or even a desired behavior in robotics.
And the workhorse method for text-to-image synthesis, the one everyone uses, seems to be classifier-free guidance, CFG. The genius of CFG seems to be that you don't actually need a separate classifier model. The diffusion model does it all itself.
That's the clever trick. The model is trained to handle both conditional generation, using the prompt dollar, and unconditional generation, ignoring the prompt or using a null prompt simultaneously, often just by randomly dropping the condition during training sometimes.
Ah, okay. So it learns both modes.
Right. Then during inference, CFG uses the difference between the score estimate when conditioned and the score estimate when unconditioned. It basically calculates the direction the condition wants to push the sample in, which is a CG jolt. Then it adds that direction back to the conditional score, scaled by a guidance strength parameter, usually called omega dol or guidance scale. The guided score is approx plus omega. And that omega parameter lets the user dial up the guidance strength, right? Make the output stick closer to the prompt.
Exactly. You can trade off diversity for prompt fidelity.
It's an incredible hack, really. It achieves the effect of using a separate classifier to guide the diffusion, but without the cost or training burden of actually having one. However, we've all seen what happens when you crank that omega tau, the guidance scale, too high. You start getting weird artifacts, oversaturated colors, distorted textures. Why does the theory predict this degradation? Yet, theory does confirm that excessive guidance strength, large omega or related parameters like DDLR, can lead to these kinds of nonlinear negative effects. Remember, the score function is guiding the sample toward high probability modes in the data distribution. When you increase the guidance strength omega, you're essentially amplifying the difference vector. You're pushing the sample very hard in the direction indicated by the condition dollar.
So you might be forcing the sample into a region that's very high likelihood according to the condition, but possibly quite low likelihood according to the unconditional data distribution the model was trained on.
Precisely. You're forcing the sample potentially far away from the regions the model knows well from the general training data. This can cause the effective probability distribution being sampled from to become distorted or even break apart. Imagine you have a smooth distribution like a Gaussian mixture. If you apply extremely strong guidance towards one component, the math shows the optimal point can actually split into two symmetric lower probability points away from the original mode center. So the quality degrades because the model starts generating features or combinations that are mathematically plausible under the strong guidance force, but structurally nonsensical or unlikely based on the actual training data, things that didn't exist in reality.
Okay, that makes sense. Pushing too hard breaks the underlying structure. Now, the versatility of these conditional models has pushed them way beyond just static generation like images. They're now moving into really complex sequential domains like reinforcement learning, RL, and planning.
This is a really exciting and major paradigm shift happening right now. In classical RL, you typically iterate, estimating value functions or policies using things like Bellman updates. It's often step-by-step. Diffusion models offer a completely different perspective. They treat sequential decision-making as pure generative sequence modeling.
How does that work in practice? Is the entire sequence of states and actions treated like one big high-dimensional image?
In essence, yes. That's a good analogy. A trajectory is just a sequence of states and actions. OS dollars, ANS1, A1, SHAH dollars. You can stack this entire sequence into one massive vector. Then you can train a conditional diffusion model to generate these trajectory vectors. The goal becomes modeling the conditional distribution where Gary represents some desirable outcome or property of the trajectory. Usually something like achieves a large cumulative reward.
So models like diffuser or decision diffuser, they're basically learning the score function for entire trajectories, conditioned on achieving high reward or satisfying certain constraints or exhibiting specific skills.
Exactly. They are often trained on large offline datasets containing a mix of successful and unsuccessful trajectories. Then, during inference, instead of iteratively calculating the next best action based on a learned value function or policy, the diffusion model uses its learned conditional score function to sample an entire coherent trajectory tau that is likely to satisfy the condition, e.g. high reward.
That sounds remarkably efficient for planning, especially long horizon planning. It generates the whole plan in one go, rather than step-by-step decision making.
It can be, yes. It generates global, long-horizon solutions directly, leveraging the power of the diffusion process to ensure consistency across the whole trajectory.
And this idea naturally extends beyond RL into general black box optimization, right? If the conditioning guidance is just summarized by some objective or reward function, well, whether it's finding optimal parameters in chemistry, robotics, finance, whatever, the DM essentially acts as an optimizer.
It acts as an optimal solution generator. The DM learns to sample solutions, the tau, which could be trajectories, parameters, molecular structures, etc., from the conditional distribution, pi of Dale, where is some target value or level for the objective function, to Daller. It generates solutions that are predicted to yield exactly that reward level y, while also respecting the underlying structure and constraints learned from the training data. The DM acts as a powerful prior, generating high-fidelity solutions that look like plausible solutions from the domain.
But the challenge we just discussed with classifier-free guidance seems like it would return here with a vengeance.
Yeah.
Choosing that target reward level dollar, if we set too high, much higher than any reward seen in the training data, the model has to extrapolate, doesn't it?
Absolutely. And extrapolation in high-dimensional spaces is notoriously difficult and risky. If the target reward is significantly beyond the coverage of the training data, the diffusion model, while trying its best to generate a solution that meets that high targeted dollar, runs a high risk of producing outputs that are structurally nonsensical or invalid, like generating physically impossible robotic movements because they technically achieve the target metric, or designing molecular structures that are chemically unstable or invalid because the model is forced to venture into uncharted territory in the latent space defined by the training data.
So we need some theory to tell us how high is too high. How ambitious can we be with our targeted dollar?
Indeed. And theoretical progress is being made here, connecting the generation quality of DMs used for optimization back to established principles from optimization and learning theory. For instance, recent work shows that the quality of the generated solutions, specifically their suboptimality compared to the true optimum, can be related to concepts like the optimal off-policy evaluation error in bandit settings. This kind of relationship helps provide guidelines. Your ability to generate high-quality solutions for a target reward is fundamentally bounded by how well your training data coverage supports that level dollar. It provides a much-needed mathematical anchor for balancing aspiration, high-reward target, with feasibility, what the model actually learned from data.
Okay, we've established that the power and quality of diffusion models come from their deep grounding in differential equations and score functions. But that same physics-based generation approach also leads directly to their primary weakness, the sampling bottleneck. They can be slow.
It really is the flip side of the coin. It's the inherent cost of numerical integration. To accurately track the path defined by the probability flow ODE, or the reverse SDE, especially using basic methods, you need to take potentially hundreds or even thousands of tiny steps. This iterative process, where each step depends on the previous one, is just fundamentally slower than, say, the single forward pass of a generative adversarial network, GAN, or a variational autoencoder, VAE decoder. That makes DMs challenging for real-time applications.
So if the problem is slow numerical integration, the solution must lie in getting better at integration, right? Accelerating sampling with advanced solvers. We need to somehow slash those step counts from, say, 1,000 down to maybe 10 or 15 without wrecking the quality.
Exactly. And the first major breakthrough in this direction was DDIM, denoising diffusion implicit models. DDIM was based on a really profound insight about the training process. Remember we said the simple loss function, that mainly cares about predicting the noise correctly? Well, it turns out this training objective only really depends on the marginal distribution's PT xt months of malars, meaning how noisy the image is at time to given the original 6 malars. It doesn't strictly enforce the exact Markovian step-by-step path PXT1 gathers used in the original DDPM formulation.
Wait, so you only care that you start at $6 and end up near $6, or vice versa, but the exact path you take through the intermediate noise levels is somewhat negotiable.
That's the core idea. DDIM proposed a non-Markovian generation process. This means the next step generated, SICT1, doesn't just depend on the current state 6 balls, but it can implicitly depend on the prediction of the final clean image $6 as well. By carefully choosing this implicit reverse sampling step, they found they could skip many intermediate time steps while still ensuring that the overall marginal distribution PC dollars at the sampled time points remained consistent with the original diffusion process. Mathematically, it turns out the DDIM update step is equivalent to applying a specific numerical method, the exponential Euler discretization, to the probability flow ODE.
And that allowed much bigger time steps.
Yes, it instantly allowed reducing step counts from thousands down to maybe 50 or 100 or even fewer, while maintaining surprisingly high quality, a huge leap in speed.
Okay, DDEM made it much faster, but to get down to really small step counts like 10, 20, we need even more sophisticated tools. This is where things like the DPM solver family come in.
Right. DDIM was like using a better basic integrator. DPM solver and similar approaches are like bringing in the full toolkit of professional numerical analysis for solving ODEs. They apply the extensive knowledge base developed over decades for solving differential equations methods like Runge-Kutta, Schoen's method, Adams-Bashforth predictor correctors, but they tailor them specifically to the structure of the probability flow ODE used in diffusion models.
How do they tailor them? What's specific about the PFODE?
They recognized a key property. The PFODE is what's called a semilinear differential equation. This means you can split the dynamics, the dT/dt apart, into two distinct pieces. One, a simple linear term, often involving just 5et, which describes how the state naturally drifts towards the origin. This part is easy to solve analytically, exactly. Two, a complex nonlinear term that depends on the neural network score prediction. This is the hard part that requires numerical approximation.
Ah, so you solved the easy part precisely, and you only need to use numerical methods for the hard, score-dependent part. That sounds like a massive efficiency gain.
It is. You leverage the known structure of the equation. Another key technique used, particularly by DPM solver, is time reparameterization. Instead of taking steps that are uniform in the standard time variable, from log to t, they often map time to a different variable, usually related to the signal-to-noise ratio. A common choice is the half-log signal-to-noise ratio, often denoted lambda. Why do this? It turns out that if you take integration steps that are uniform in this lambda space rather than two-null space, the function you're trying to integrate, the nonlinear part involving the score, becomes significantly smoother, less erratic.
And smoother functions are easier to approximate accurately with fewer steps using numerical methods.
Exactly. So instead of a simple Euler step like in basic DDPM or the exponential Euler of DDIM, DPM solver uses these specialized high-order integrators. They analytically integrate the known linear part of the dynamics and use sophisticated schemes, like second-order Hune or multi-step methods, to integrate the complex score-dependent part, often in that reparameterized lambda time.
Yeah.
The result is the ability to achieve very high sample fidelity in sometimes just 10 to 15 steps. It's really state-of-the-art for OD-based sampling.
It sounds incredibly powerful. The difference between using, basic arithmetic versus calculus to solve a physics problem.
That's a fair analogy. DPM solver is highly optimized for the specific physics of the diffusion process ODE.
But does this complexity, introducing high-order numerical schemes, time reparameterization, come with downsides? Does it risk becoming more fragile or require more careful tuning of hyperparameters compared to the relative simplicity and robustness of something like DDIM?
That's a very fair point and a real consideration. Yes, generally speaking, high-order numerical solvers can be more sensitive. They might react poorly if the time-step grid isn't chosen carefully, or if the underlying score function learned by the neural network happens to be very non-smooth or noisy in certain regions. DDIM, being essentially a first-order method, exponential Euler, tends to be quite robust due to its simplicity. It might not be the absolute fastest for a given quality level, but it's often reliable. However, the significant performance jump offered by methods like DPM solver, especially when you absolutely need single-digit or very low double-digit sampling steps for real-time use, usually outweighs the slight increase in implementation complexity or potential need for careful tuning. For top speed, they've become the go-to approach.
Okay, so that's optimizing the solver for a given pre-trained diffusion model, the teacher. But the ultimate acceleration seems to move beyond solving altogether. It's about somehow learning the solution path itself, often through techniques like distillation.
Yes, exactly. The next logical step is to say, instead of relying on these complex iterative integration schemes at inference time, can we train a new, potentially simpler or faster model that learns to directly reproduce the outcome of the slow, multi-step generation process in just one or a few steps? Progressive distillation, PD, is a prime example of this philosophy. PD works iteratively. You start with a slow teacher model that takes no RAL steps. You then train a student model to replicate the result of a two-step jump made by the teacher, but using only a single step. So the student learns to predict directly from 6 days, mimicking what the teacher did in 2 steps, XT2 under XT2. Once the student is trained, it becomes the new teacher, now taking end away 2 steps. You repeat the process, training a new student to do a 2-step jump of this 2 and 2-step teacher in 1 step. You keep having the steps.
Until you've compressed the entire generation path down to maybe 1, 2, or 4 steps, whatever your target speed is.
Precisely. You distill the knowledge of the long, slow integration path into a much faster network.
And maybe the most conceptually pure approach in this distillation-like space is consistency models, CMs. They aim for genuine single-step generation, potentially even trained from scratch.
CMs are conceptually quite revolutionary, yes. They aim to directly learn the single mapping function, let's call it PSI, that takes any noisy point 6 to Zoller on any valid PSIE trajectory at any noise level and maps it directly back to the original clean data point, $6 that started that trajectory.
Right.
If you can learn this function PSI perfectly, then generation becomes trivial. Sample random noise $6 from the prior and apply the function once. $6 and apply the function once. $6 to VRT. One shot.
Wow. But how do you train such a function from scratch? If you just map noisy points to clean points, how do you ensure that a slightly noisy version, $6, and a much noisier version that both originated from the same clean image, $6, actually end up mapping back to that identical $6? You need consistency along the path.
That's the core challenge and where the name comes from. They enforce a fundamental property of these continuous flows, often called the semi-group property or just consistency. This property essentially states that the mapping is self-consistent across time. If you map from times down to an intermediate time, using PSU to the origin, the result must be identical to mapping directly from time all the way down to the origin, mathematically. The path doesn't matter, only the start and end points on the same trajectory.
Okay, so the consistency model loss function, like the LAFDCM loss they propose, must be designed specifically to minimize violations of this property, to force all points along a single trajectory to map back to the same origin, $6.
Exactly. The loss function is carefully constructed, often involving pairs of points from the same trajectory, to enforce this consistency. It ensures the model learns the correct overall structure of the inverse flow map across all time steps. This allows CMs, at least in principle, to achieve high-quality, single-step generation, completely decoupling the final generative act from the hundreds of intermediate steps usually required for numerical integration. It's a very powerful concept. #outro. So if we try to synthesize everything we've covered today, I think the big story of diffusion models is how they achieve their breakthroughs by reframing a notoriously hard problem, high-dimensional density estimation, into essentially a physics problem. A problem governed by stochastic and ordinary differential equations.
Right. It feels like translating a problem into the language of physics and calculus.
Exactly. And that translation allowed the field to leverage an incredibly powerful set of mathematical tools that weren't easily applicable before. Score functions, Ito calculus, connections to statistical mechanics like Tweedy's formula, and the entire arsenal of advanced numerical solvers for differential equations. That's what led to the unprecedented sample quality and fidelity we see.
And then the second major piece was the flexibility unlocked by the conditional frameworks like classifier-free guidance. That extended DMs far beyond just static image generation. They've become these dynamic tools capable of modeling complex planning in RL, acting as general-purpose black box optimizers, and really fundamentally restructuring how we even think about generating sequences or making decisions in complex domains. They're arguably the most versatile class of generative models we have today.
Agreed. And this relentless pursuit of quality and stability naturally led to the current intense focus on speed. We traced that evolution from the initial slow integration of DDPM to much faster ODE solvers like DDIM and DPM solver, and finally to methods like progressive distillation and consistency models that aim to skip the integration path entirely. All these speedups, from DDIM through to CMs, can be seen as different attempts to find or approximate the fastest, most efficient possible flow between the chaos of pure noise and the structured creation of data.
Which seems to bring us right to the final, deep, and still very much active theoretical question: the precise relationship between diffusion models and the theory of optimal transport, OT. Optimal transport theory is all about finding the most efficient way to move probability mass from one distribution, like our simple Gaussian noise, prior to another, like the complex data distribution. It seeks the path with the minimum effort or minimum kinetic energy, often called the straightest line, or the Monge map between the two distributions.
Right. And here's a crucial point. While the probability flow ODE that current diffusion models learn to solve is guaranteed to transport the prior noise distribution to the target data distribution, It is generally not the unique minimum kinetic energy optimal transport map. The path the DM flow takes, guided by the learned score function, definitely works. It gets you from noise to data. But that path might be unnecessarily curvy or circuitous from a pure physics or minimal energy perspective. It's a valid path, but likely not the most efficient one mathematically possible.
So the provocative thought for you, the listener, to maybe explore is this. Is the current intense quest for ultra-fast, even single-step diffusion model generation through methods like rectified flow, reflow, which explicitly tries to minimize an upper bound on the kinetic energy of the flow, is this quest ultimately a search for finding the true global optimal transport map between noise and data?
Could it be that if we could find that mathematically straightest minimal energy path, the generation process itself would become conceptually instantaneous, a single direct mapping requiring zero iterative integration effort? How close are we to truly unifying generative modeling with the fundamental principles of transport theory? And what new insights into the physics of data generation might we discover by studying that truly optimal trajectory? That intersection of generative modeling, differential equations, and optimal transport that feels like where the next really fundamental breakthrough in this field might lie.
A fascinating place to leave it. Thank you for joining us for this technical deep dive into the mathematics and architecture of diffusion models. We'll see you next time on the Deep Dive.